Hi everyone. Today we're going to look at a notation that mathematicians invented to make something that was really repetitive, that showed a really nice pattern, a little more streamlined. And it's called sigma notation. Mathematicians have done this all the time, instead of writing 3 plus 3 plus 3 plus 3, right? That gets repetitive. Mathematicians have created the multiplication symbol. So if I had 4 threes here, we'd go, instead of that, we'd go 3 times 4. Or same thing with, if I have 2 times 2 times 2 times 2 times 2, and that's really redundant. So mathematicians created exponents to shorten that process up. So what we're going to look at is a way to shorten up a sum of a number for which there's a pattern or a commonality within. So that is called sigma notation. So we use the Greek letter sigma, which is the Greek letter for S, capital S, to indicate sum of a particular number of terms in the sequence. A sum of a sequence, what we're going to be writing out here, is what's called a series in math. And this notation looks really fancy, but if you know how to read it, it's not that big a deal. The 1 down at the bottom and the 4 up in the top are called indices. Those are indicators of how many terms there are. So call that the lower index. And then that 4 is what's called the upper index. And index is just another word for organizing or counting. And then the R is a really simple formula, but this is a formula for the sequence. We might have had this before, like A sub R equals R. And that would be a formula for the sequence. And we'd say, well, what's A sub 1? Well, that would be plug in 1 for the expressions. That would just be 1. What's A sub 2? And so on. So this is a formula for the sequence that we're going to be adding up. And the lower index and the upper index are the indication of which terms in the sequence. So this is going to add up terms 1 through 4 in the sequence defined by this really simple expression. Those can be much more complicated, and they usually are. So in this case, this would be when A sub 1, when R is 1, that would be 1, plus term 2 in this sequence. We're going to plug in 2. And then term 3 is going to be 3. And this formula, this expression, it just says add up the first 4 terms in the set of counting numbers 1, 2, 3, 4. And we add those up and we get 10. And 10 is what we call the value or the sum of this expression in sigma notation. So we're going to look at just a couple examples. These are all in your homework questions that you have to do in a big box ahead of each set of exercises, so these should look familiar. And you'll notice that the notation changes the numbers on the indices, and then the formulas are going to change. And that's really all that is going to change in this notation. So I'm going to do the first couple just really detailed. You certainly don't have to do this as detailed as I do. So our indices here are going to be summing from R equals 1 to R equals 4 of the sequence defined by R squared. And so what I usually think about in my head, and I'm going to write down right here, is, well, when R equals 1, what is that term going to be? Plus, then we're just going to add when R equals 2, what is that term? Plus when R equals 3. And then when R equals 4, that is our last value, as we can see in our upper index here. And so we're just going to substitute 1 into R squared, our formula for the sequence, and we're going to get our value for our series. So this is just going to be 1 squared plus R equals 2. That's going to be 2 squared. R equals 3. 3 squared. R equals 4. That's 4 squared. So this just says 16 plus 9 is 25 plus 4 plus 1. And so we get a value for this series of 30. Second one's just a little more complicated, and you just have to make sure you're reading this notation carefully. We're starting not at R equals 1, but the variable in our formula has changed to k, so we're starting out at k equals 2 up to k equals 4, and this actually simplifies things for us. There's one fewer term that we're going to have to add up here. So the expression is k times k minus 1, so same thing when k equals 2. And we're going to add to the value when k equals 2 what we get when k equals 3, and so on up to k equals 4. This is our last index. And so k equals 2, that's just 2 times 2 minus 1, which is 1. When k equals 3, 3 times 3 minus 1, which is 2. And when k equals 4, 4 times 4 minus 1, which is 3. So this just says, again, 12 plus 6 plus 2. And we get 20. There's the value of our series there. In statistics, a lot of times variables that we're measuring, say it's a bunch of heights or it's a bunch of people's IQs or how much change is in your pocket, we use the same variable, but we use a subscript to say which person we're talking about. And so this notation looks a little goofy, but we're not going to get a number answer when we write this series out in this notation. So it's the same thing. We're going to start out when I equals 1 up to I equals 3, but the expression has x with an I in the subscript. So we're just going to treat this like a function. When I equals 1, your term, we don't know a number value for it, it's just x sub 1. And then we're going to add to it when I equals 2, and we're going to keep on going until we get to our upper index, which is just 3. So writing out this series, there's no number answer for it, but this series says for your x variable, whatever it is, add up terms 1 and 2 and 3 and give the total. And again, like x sub 1 could be person 1's height, and x sub 2 could be person 2's height, and so on. And so, if I want to say add up a bunch of people's heights, I have a quick shorthand way to do it. It doesn't give us a number in this case, but it gives you direction. You notice there's lots of variables in the second expression. Our lower index is 1. Our upper index is the variable n. And so we're not going to have a definite ending value on this. We're going to add up when k equals 1. What k is in the subscript, so this is y sub 1 plus, and we're going to keep going until I get 2. Well, the upper index is not a number, so we're going to just establish a pattern. We're going to put a little dot, dot, dot in there, and we're going to say this keeps on going up until we get up to y sub n. Now, here's a use for this. So we have some measurements of x's, and you can imagine that these x's could be how many hours a student studied for a test, and then the y's might represent for those same students, student 1, student 2, student 3, and student 4, how many questions they got wrong on the test. So these aren't going to come up with meaningful answers, but we are going to get number answers for these. So this is the same kind of expression we had on the page before, from 1 to 4. So this expression says x sub 1 in the subscript where the I goes, plus x sub 2 plus x sub 3 plus x sub 4. And now if we look up here, they gave us what these values are. So this is just saying to us add up the x 1, 2, 3, and 4 up top there. So this is 2 plus 5 plus 3 plus 4. Those are the values for x sub 1, x sub 2, x sub 3, and x sub 4 up top. And so there we get 14. And those would be the total, in this case, hours that students studied for this test. Now down here, there's a little computation that we're going to have to do with the x's and the y's. Again, we're starting at 1 and going to 4. If this said 2 down here, we'd start at 2 and go to 4, etc. But this starting at 1 says we're going to do x sub 1 plus y sub 1. Now I'm writing this out. If I were trying to calculate this, I would probably go right up here and just grab those numbers. Now we're going to go when k equals 2, what our value is. So this would be x sub 2 times y sub 2, and so on. We're just going to keep repeating this, changing the value of k until we get up to that upper index. And so we'll just plug those values in. So x sub 1 is 2, y sub 1 is 4, x sub 2 is 5, y sub 2 is 1, x sub 3 is 1, y sub 3 is 6, and x sub 4 is 3, and y sub 4 is 2. And so we get a total of 8 plus 5 plus, I can't read, there's a little watermark there, 8 plus 5 plus 6 plus 6. So we get 13 plus 12, 27. Check my math there in case I messed that up in my head. So that's really all there is to sigma notation. You'll see a lot of these examples worked out on your assignment for today. And hopefully, if this got really easy for you, you fast forwarded and followed my work through. You certainly can do that with all of these videos that we have while we're doing this online learning. So I hope that was helpful. Let me know if you have any questions.